In this section, we'll be talking about rational functions and their graphs. And those graphs are some of the most interesting in mathematics because there's a great variety of graphs that come from rational functions. Now, rational functions are composed of a polynomial numerator over a polynomial denominator, like this example. Now, because we have a polynomial denominator, we have variables involved, and those variables can take on values that will cause the denominator to become 0. And if the denominator becomes 0, the entire fraction is undefined. That presents a rather interesting situation graphically, as we'll see in just a minute. We're going to begin our discussion and our investigation of the graphs of rational functions by using the point plotting method. Now, we know that if we replace x with 3 here, we have a y value that's undefined. Now, I have just given a number of other points that we can plot here in our table. I've plotted those points and some others here on this coordinate plane. Now, notice that the graph is curvy right over here, and it's kind of curvy in the same way over here. And it turns out that the last point down here on this curve does not connect with a point way up here. So the graphs of rational functions are very often not continuous. Well, let's see. The graph then looks like this. It's kind of a curvy thing going on. This is called a branch, by the way. This is a branch of the graph. Here's another branch. Now, it turns out that these branches are approaching lines which are called asymptotes. Now, the vertical line that the graph is approaching, the vertical asymptote, is at the 0 of the denominator of our function. Now, that was x equals 3. X equals 3 is here, and that vertical asymptote then is this line. Now, an asymptote just generally is a line that the graph gets infinitely close to at the extremes of the coordinate plane. Now, by the extremes of the coordinate plane, I mean extremely left, extremely right, extremely up, or extremely down. That is, as this graph drops, it will get closer and closer to this line, this vertical line, x equals 3. And as this graph goes infinitely far upward, it'll just snuggle up to that vertical asymptote. We'll see why in just a minute. This particular graph also has a horizontal asymptote, and that horizontal asymptote is at y equals 2. And once again, it's an asymptote because the graph gets infinitely close to that line at the extremes of the coordinate plane, left and right. Now, let's see why that's the case. Let's see why the graph gets really close, and it's by the nature of the function itself. Now, the function, it's written over here, but I'm going to repeat it right here. It's y equals 2x over x minus 3. Now, think about what happens to this quotient as x gets really, really big. Like, let's say x takes on the value 1,000. So we would have 2 times 1,000. That's 2,000 for the numerator. And in the denominator, 1,000 minus 3. So this is about 1,000. That's about 2,000. So this quotient is about 2. But this denominator is just a little bit smaller than 1,000. And therefore, this quotient is a little bit larger than 2. So as x goes out to 1,000, you see f of x, the y value, is just over 2. It's just on top of that line. And no matter how far we get out there with the value of x, 1,000,000 for example, this quotient is still just a little bit bigger than 2. And that difference between 2 drops as x gets bigger, 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 bigger. Okay, so that's why we get that effect of the graph getting really close to that horizontal asymptote. Same is true in the negative direction. Now, what about the vertical asymptote? Let's see what happens as x gets really close to 3 from either side of 3. Now, as x approaches 3 from the right side, we consider numbers that are a little bit bigger than 3. Now, look at what happens here. A little bit bigger than 3 in the numerator times 2 is a number a little bit bigger than 6. So it's 3, let's say 6, let's say plus, 6 plus. All right, in the denominator, a little bit bigger than 3 minus 3 is a small number. And the closer we get to 3, the smaller that number is. So this is a tiny number in the denominator. And it's getting tinier and tinier as x gets closer and closer to 3 from the right side. Okay, tiny goes into 6 a lot of times. And the smaller this number gets, the more times it'll go into 6, you see. So this is becoming bigger, bigger, bigger as x gets closer, closer, closer to 3. Now, no wonder then the y value, as we get closer and closer to 3, the y value is going further and further up. You see, and in a similar way, from the left side, it gets further and further down, because from the left side, a number a little bit smaller than 3, a little smaller than 3 minus 3, this tiny number happens to be negative, and so the quotient then will be negative. Okay, so that's what's going on graphically for the asymptotes. Let's talk about it from an algebraic standpoint and describe the notion of asymptote that way. It's this, that as x approaches infinity, f of x is approaching a fixed value. So as x is getting really, really big, f of x is approaching a single value. And that gives us a horizontal asymptote, and that asymptote is at y equals 2. Now it turns out that as x approaches infinity in either direction, that is plus or minus infinity, this is what's going on, and we have that horizontal asymptote. Now, symbolically, this is what's happening for a vertical asymptote. As x approaches a single value, like 3, f of x is approaching infinity. Now, notice the juxtaposition here of the single value and the infinity notion. As x approaches a fixed number, f of x is approaching plus or minus infinity. That gives us a vertical asymptote and sometimes vertical asymptotes. And in this case, it's x equals 3. All right. In graphing rational functions, it's the identification of asymptotes that's really important, because since the graphs kind of get infinitely close to them, we can almost draw those branches just by looking at asymptotes. If we kind of know roughly where they are, the graph is pretty easy from that point. So the first thing we want to do is identify asymptotes. So here's the first order of business when we graph rational functions. Number one, we want to identify vertical asymptotes. Now, the vertical asymptotes, remember, are simply at the zeros of the denominator of the rational function. That's all there is to it. So what we'll do is take the function and just factor everything in sight. Now, we don't need to factor in the numerator, except that it helps us a little bit to find values to plot later after we identify the asymptotes. We need to factor the denominator to give us the zeros for those vertical asymptotes. So here, the vertical asymptotes are the lines, which are the zeros here. They're y lines now, and the 0 corresponding with this factor is 4, corresponding with this factor is negative 2. So y equals 4 and y equals negative 2 are the vertical asymptotes. Now, for the horizontal asymptote, it's kind of interesting. There's only one of those, and it's identified according to a comparison of the degree of the polynomial numerator to the degree of the polynomial denominator. Now, degree corresponds with exponent and that kind of thing, recall. Now, just consider a couple of examples here. If we have, now notice here, we have a 0-degree numerator and a 1st-degree denominator. Now, we're talking about which one is larger here. The degree of the denominator is larger than the degree of the numerator. And over here, same idea. The degree of the denominator is bigger than the degree of the numerator. And when that happens, when in either of these cases, anytime that happens, the horizontal asymptote is the x-axis itself. And therefore, it is the line y equals 0. Okay. So a comparison of degrees. Now, we have two other situations to consider. The first situation we considered is where the degree of the denominator is larger than the degree of the numerator. Now let's consider the situation where the degree of the numerator and denominator are identical. All right, so here, f of x is, now notice, 2nd-degree numerator, 2nd-degree denominator. And over here, a 1st-degree numerator, 1st-degree denominator. We had this kind of condition in the original example that we had. It was, I'm going to read it over here, it was 2x over x minus 3, 1st-degree numerator and denominator. Okay, here's how we identify the asymptote, the horizontal asymptote. It is simply the fraction composed of the leading coefficients. Now, the leading coefficient in the denominator is understood 1, and look at this. We have a y line which is 2 over 1, or simply y equals 2. In our example over here, the horizontal asymptote was 2 because it's 2x over 1x in the denominator. So again, 2 over 1. Here, the horizontal asymptote is 3/5 because it's the fraction y equals 3 over 5. Now, the third situation is a situation where the degree of the denominator would be smaller than the degree of the numerator. And in that condition, we have a slant asymptote. And I'll tell you later how to calculate the equation for the slant asymptote.